Okay, I think it's time to start. So I want to welcome you all back to the auditorium for this afternoon section. And today we're going to have in the first talk of the afternoon, the talk of Professor Daniel Kleppner. And Professor Daniel Kleppner is a professor of the Massachusetts Institute of Technology. He's a Lester Wolf professor, and maybe he's one of the most important person in atomic physics, but he's a nice person, you know. He's a nice teacher, and he has so many prizes that I'm not going to list here, and he doesn't like long introduction anyway, but he's a guy that knows where science is going and know how to motivate young people, and he's been motivating a lot of young people because he has a lot of students that pass to his guidance that help to make the atomic physics that we are living today. And Professor Kleppner himself basically start all the important fields like cavity QED for atoms, cold atoms, Bose-Einstein condensation, and he gave the seminal ideas with the group of students and researchers. He guided in the back to the years where this start. Evaporative cooling was one of the important ingredients for everybody to reach condensation, and still today, very well applied, is a way to reaching a lower temperature we need. Professor Daniel Kleppner is still a leader, and of course he is the one that has been passing through many parts of the history of atomic, molecular, and optical physics. He's been the leader of those fields for a long time, and his talk today is the deep history of AMO, atomic, molecular, and optical physics. And I want to thank you, Dan, for accepting giving a talk for this school. We all would like to have you here. We had you here in this auditorium a few times, and always been very exciting. But I hope that in the coming future, we're going to meet again here and have you live and in three-dimensional, giving us a new talk. That's always very good. So please, thank you for accepting, and now you can go on with your talk. Thank you.
Well, thank you very much for inviting me to your meeting. I wish I could be there in person also. My visits to Brazil have always been wonderful events, but I have to talk to you remotely today. The title of the talk, The Deep History of AMO Physics, explains that this is a talk on history. It's a talk in a history of AMO physics. Part of the reason is people may not know what AMO means. Is it a person, a place, a subfield of physics? I want to describe what it is and how it came to be. And the reason I call it a deep history is that AMO physics generally starts with the names of Otto Stern and I. Robbie. And I want to go a little bit back beyond that. So the talk has two parts. The first part is going back to the origins and how it grew. And the second part is what happened to those origins and how the field has evolved. And there's a little preface, which is this: how AMO physics came to be. First of all, AMO stands for Atomic, Molecular, and Optical Physics. The title was formalized in 1978 when the American Physical Society created the Division of Atomic, Molecular, and Optical Physics, DAMOP. So at least in the United States, AMO has a very specific, well-defined meaning, but it's common in the field, and most international organizations or physical societies sort of recognize the category. It descended from the American Physical Society's first division, the division of electron and ion optics. And that's kind of an interesting division because it was the first division in the American Physical Society, and it was founded in 1943. And the first chair was I. Robbie. He was the president of the Physical Society at that point. But it's a very curious event. In 43, the war was still going on. Robbie was directing the research at the MIT Radiation Laboratory, where they were developing radar under conditions of very top secrecy. And the first division was action.
Then we
Am
we
I-
have,
am
we
I- Well,
go ahead. We solved the problem.
all right. Anyway, the first division was devoted to electronics and electron power sources. And why you would do that in the middle of the war was a total mystery. No one seems to know why. So we started out in a mystery, but it was directed by Robbie. Now, Robbie had been mentored by Otto Stern in Hamburg starting in 1927. Robbie just got his degree from Columbia University, went to Europe because he knew there were interesting things going on, but he wanted to see for himself. He ended up working with Stern at the University of Frankfurt. He went actually to work with Wolfgang Pauli on theory. They got on very well together, but Pauli said, why don't you walk around and see what else is going on in the department? And he happened to walk into the laboratory of Otto Stern, became interested in what Stern was doing, came up with a proposal for a new method for deflecting atoms. Stern said, why don't you try it? So Robbie did it. He'd never done experimental physics before, but it worked, and it converted him on the spot from a theoretical physicist to an experimental physicist. Now, Otto Stern became prominent in the Stern-Gerlach experiment that really staggered the physics community in 1924. So the first part of the talk here is what happened then. This is planting the seeds of AMO. Acknowledgement. This book is the really proceedings of a fete for Otto Stern, which was held 2 years ago in the University of Frankfurt. The editors of the book, Bertislav Friedrich and Horst Schmidt-Wacking, have a chapter in the book, which is a beautiful scientific biography of Stern, and I've drawn heavily on that in what I've learned that's new that I'm presenting. The book is open access. You can download it. You can't print it, but you can read it. And I think that's a wonderful thing. So the history starts with the Stern-Gerlach experiment. Now everyone learns about this in when you start studying about atomic physics. Here's a little picture of it. And there is the result of the first time this experiment worked in November 1922. This is a famous blob. It's famous because of the white space in the center. According to classical physics, that couldn't be there. Everything would be black. And the fact that you see so clearly that the atomic beam is split into two halves was a sensation. It was staggering. Even Stern was amazed. He had expected the experiments to fail. No one really thought it would work because it was so peculiar. Namely, it was proof of the existence of quantum states, which had different geometries. Robbie told me about the time he went to work with Stern. He said, 5 years after the invention, the discovery over there, people were still coming in to look at the apparatus for itself. They could hardly believe it. But why all this fuss? Well, classical physics was having trouble. There was a lot of trouble. Only a few people were really worried about it. Trouble was, it started in 1900 when Planck suggested the idea of a quantum. But Planck never really believed in it himself. He thought it was just a mathematical manipulation, and he didn't talk about it. He gave lectures at Columbia University in 1908 on theoretical physics, and this was barely mentioned at all. Planck just couldn't make heads nor tails of what was going on. Einstein understood. He didn't base his thinking at all by Planck's work. He thought it from the beginning and realized that it had to be a necessity. He wrote his results on the photo effect called an heuristic theory of photoionization. Heuristic means that it's something impossible, but you used it just as a crutch without actually believing in it. And that was stuck with Einstein really throughout his career. He was never satisfied with quantum theory. Nonetheless, he used it for many purposes and used it beautifully. In 1907, Rutherford announced radioactive half-lives, and the question came up, if you have a gas of radioactive atoms, how does each atom know when it's time to decay? It's the same question as the question is, how does an atom going into the Stern-Gerlach apparatus know whether it should go to the right or to the left? Bohr's paper on the hydrogen atom was a real triumph in quantitatively explaining the hydrogen spectrum, but it was based on totally unjustified and rather absurd assumptions. But it worked well. Bohr himself understood the situation. He confessed that the assumptions he made there were absurd, but that they would be clear one day, and he actually guided the field into the development of quantum mechanics. There was the Frank-Hertz experiment, which showed stationary states of molecules. Millikan's photoionization experiment, measuring the rates predicted by Einstein was beautiful. There are all these things telling you that something is deeply wrong in classical physics, but nobody could offer any explanation. Well, the fuss about the Stern-Gerlach experiment was uniquely weird. It was weird because without knowing anything much about the experiment or having to interpret the data spoke for itself. There is no way to deny what you were seeing, and people couldn't believe their eyes. This problem, how does the atom know which way to go on the right or left, was inherited throughout the history of quantum mechanics. And it was the basis for many arguments which can continue to today. Well, classical physics was about to fall, and the Stern-Gerlach experiment attracted the whole community into these issues. It gave intolerable results. Classical physics had to fall. The fall came rather quickly. In 24, Louis de Broglie proposed matter waves. In 25, Davis and Germer detected matter waves. Heisenberg and Jordan that year formally presented matrix mechanics, the first quantum theory. The year after, Schrodinger showed his wave theory and showed that the two theories were equivalent. So quantum mechanics had arrived. So I want to jump ahead now by 20 years. In 43, Stern won the Nobel Prize in Physics for his contributions to the development of the molecular array method and his discovery of the magnetic moment of the proton. Question, why is there no mention of the Stern-Gerlach experiment? I was deeply puzzled. I thought that the prize committee must have just been so confused about all the developments in quantum mechanics that they simply overlooked that. It's not the case at all. Now, it turns out that during his career, which was only 12 years long, in that relatively brief career, his achievements included 6 Nobel-class discoveries, which I hadn't really appreciated. First, the measurements of molecular speeds was the first time that one could show that individual molecules, rather than their group averages, could be seen in detail. It confirmed the physics of Maxwell's equations and statistical mechanics. One was the Stern-Gerlach experiment, which I've talked about. He demonstrated recoil from absorption of a photon. This was a critical component in Einstein's theory of emission of atoms, absorption and emission, which underlies the laser. It was a very difficult thing to do before lasers. The spectral densities of gas discharge sources was very low, but he made the experiment. He did the experiment actually with Otto Frisch, who was his graduate student. And Frisch, of course, is one of the co-discoverers of nuclear fission later on. He measured the first demonstration of atom diffraction. If atoms are waves, then they ought to diffract from a periodic structure just like light does. And he did that experiment. He discovered the anomalous magnetic moment of the proton. which is a way of saying he discovered the strong force. The only forces known before that were electric and magnetic, and the strong force was something different. And that was really earth-shaking, and that's what he got the Nobel Prize for. He also discovered the magnetic moment of the neutron, which is a great puzzle because the neutron is strictly neutral, but apparently it has charges inside it which can give a magnetic moment. So it's not an exaggeration to say that any of these were worth Nobel class physics. Stern was a fantastic person. Stern's first academic position was assumed in 1912. He had just gotten his habilitation, his degree. It was with Einstein. He was Einstein's first research assistant. And my belief is that that period was only a couple of years, was what really molded him as a physicist and made him the great person he was. He went to work with Einstein at the University of Prague. That was Einstein's first position. And he took on Stern as his first assistant. So he was Einstein's first research assistant. They quickly moved to ETH in Zurich and worked together there for about 2 years on thermodynamics and statistical physics. But in 1914, the war came, their academic work stopped, and it resumed only 5 years later for Stern. But these making about this being a deep history is that that Einstein was behind Stern, and that Stern reflects the very best qualities of Einstein. His skill at identifying important problems. I mean, that's amazing to get so many really important problems that quickly. The clarity with which he addressed the issues was very reminiscent of Einstein, and the energy with which he attacked the problems. These are all reminiscent of Einstein. Segre wrote a memorial memoir after Stern died. He prepared it for the National Academy of Sciences, and he wrote this. I'll let you read it for yourself. This is very high praise from someone who was in a very good position to judge the whole community. Then I would like to talk about Robbie, and I will just talk about him. He came to work with Stern, as I described, casually working into the laboratory and becoming very interested in the work there. He was only there for about 2 years altogether, but that totally changed his career. He returned to the United States in 1929, and in 1930, he assumed a position at Columbia University, which had no atomic physics at all there. He had to start building up a new group. He was a very energetic person and managed to do that while having a huge teaching load dumped on him by the department, because that's what they did with young professors, at least in those days. But he got right to work. In his first year, in 1931, he published a paper with this diagram in it. It's the Bright-Robbie diagram. Gregory Bright was a theoretical physicist, a young theoretical physicist in the department, and they published this chart of the energy levels of a spin 1/2 electron in an atom with a nuclear spin, which could be anything. In this case, it was 7/2. By exploring this diagram, you could learn a lot about nuclear physics. You could learn about magnetic moments of nuclei. And that's what Stern did. In fact, that was the whole field of this branch of atomic physics of molecular beams, was really nuclear physics. And just using this diagram and making use of the fact that the magnetic moments of the atom as a whole varied with the magnetic field, you could extract information, you could measure nuclear spins, and you could get their magnetic moments, but not too accurately. Now, in thinking about this, he invented molecular beam magnetic resonance. This is a picture of two Stern-Gerlach magnets with a little area in between, and trajectories of the atoms depending on the orientation of their spin. If they had the right speed, they could come through this apparatus and go to the detector on the right. But if they were to change their orientation as they went through the apparatus, they would miss and you wouldn't see them. That little region in the center was a region where the spin could be clipped by the absorption of radiation. And that's the whole basis of molecular beam magnetic resonance. Here is a picture of one of their early resonance curves. In this case, you're varying the frequency, not by sweeping the oscillator, but by sweeping the magnetic field, but the effect is the same. This is an extremely sharp resonance. It revolutionized these studies of nuclear magnetic moments. This was called magnetic resonance spectroscopy. It's a form of spectroscopy. Apparently, Robbie didn't recognize that. Norman Ramsey told me he had to argue with Robbie to say that this really was a resonance curve. This statement here, let me just read the end of it. From Stern and Pauli, I learned what physics should be. For me, it was not a matter of more knowledge, but a sense of knowing when a problem is good and when it is not so good. I never knew Stern to work on an unimportant problem. That was the part of Stern that Robbie carried away and transmitted to the field. And this is foundational to the culture of AMO physics. So I would like to demonstrate just how powerful that culture is. And I'm going to do it in a rather breathless fashion. I'd like to draw a Robbie tree. Now, the Robbie tree was a diagram, picturesque diagram of everything which grew out of Robbie's work. At the foundation of the tree, right over there, is Otto Stern, and there are a few other people who contributed. The tree, much too large and dense to show here, you can't see any of the names of it, but you can believe that it is incredibly broad. This was drawn up really at the behest of the Office of Naval Research, which wanted to show how valuable the research that they were supporting was. So the problem is, how do we show the Stern Robbie tree today, what grew out of their work? As a bit of chronology, when Robbie came to Columbia University in '31, Stern had to flee to the United States to escape the Nazis. He went to what is now Case Western University. Stern never recovered his momentum. His research just kind of tapered down in this country. But at the same time, Robbie's was flowering with the invention of molecular beam magnetic resonance. So in a sense, their research stream was one. And this is why I always refer to Stern and Robbie together. They were the generating force for AMO physics. Well, what I'm going to do is just quickly go through a list of all the Nobel laureates in AMO physics and show how directly they were connected to this route, which was started by Stern and Robbie. These all had direct connections to Robbie. For instance, Norman Ramsey was Robbie's early graduate student. Famously, when Ramsey went to work, asked to work with Robbie when he went to Columbia in 1935, Robbie discouraged him. He said that molecular beams are pretty much finished. A few months later, he discovered the magnetic resonance, and the field was just starting. So there is a direct connection. Now, I was Norman Ramsey's student, which made me sort of a scientific grandson of I. Robbie. Bill Phillips, who talked this morning, was my student. So Bill Phillips is on the diagram with me in sort of an intermediate position. The others that I will talk about are all connected to Robbie, possibly in some case by people who they worked directly for them. The point I'm trying to make here is the huge influence of them on AMO physics, and by inference on physics as all. The problem, of course, is that there are more worthy candidates for the Nobel Prize than are ever given. So this ignores everyone else, which gives a very distorted view of everything. But I'm trying to give a summary of the effect on the field. And this is the best thing I could think of. First of all, on the tree at that basis was Stern, given in 43. Robbie got it the following year. They were both given at the same time in New York City because the war was still on. In 1955, Willis Lamb and Polycarp Cush got the Nobel Prize basically for starting serious work on the theory of quantum electrodynamics. In 1966, Alfred Casler was awarded the prize. Now, Casler is not on the chart. Well, he is on the chart, but with kind of dotted lines. And the reason is that he never worked with Robbie. He could have, but he couldn't get into the United States after the war. It was during the communist scare, and he was denied a visa by our State Department. Nonetheless, he was very familiar with Robbie's work. Many of his students did go to work in the United States. And he started a separate branch of AMO physics, the branch based on optical pumping, which has flourished then. It's a very strong branch in the field. So I classify him as one of the founders. Here is Bloch and Purcell, who invented nuclear magnetic resonance in 1951. Well, they actually just a few years before it. The prize was given in 1951. NMR has transformed medicine. It's given MRI imaging. It's used extensively by chemists. Purcell worked at the Rad Lab during the war where Robbie was the head of scientific, the scientific program, so they knew each other very well. So he is firmly on the tree. Bloch was at Stanford University after the war working on nuclear physics and realized that the NMR could be detected in a different way. So the two of them shared the award. 1964, Towns won the prize. He won the prize for discovering what they call the Maser laser principle. In a sense, the prize came too early because although the idea for the laser came out of the Maser, it was the laser which actually transformed the world. Towns was working at Bell Laboratories in New York City, and Robbie recruited him to Columbia, and he did his work on the Maser there, and then continuing on the laser. So this is an example of Robbie's incredible talent for seeking talent. For instance, he brought in Willis Lamb to his laboratory from across the country. And altogether, he appointed 7 faculty members who won the Nobel Prize for work they did in Columbia. So he was remarkable in his understanding of scientific quality. Here we have Bloombergen and Arthur Shallow got the prize in '81. Bloombergen worked with Purcell directly. Shallow worked with Towns, who worked for Robbie. So there are their connections. Ramsey was one of Robbie's early graduate students. He got the prize in '89, which is rather delayed because he could have been awarded this for what he called the separated oscillatory field method in 1950. So we waited about 40 years for the prize. Actually, he wasn't waiting for the prize. He was very cheerful about it. When he did get it, he was, of course, naturally happy. But he said he got it at just the right time in life. He would not need to be distracted from research by all the things Nobel laureates should do if they're good laureates. But he was free to do whatever he wished. Anyway, it was given for the prize and its use in the hydrogen maser and other atomic clocks. And I was a student working with Ramsey on the hydrogen maser. The next one was for laser cooling. This was done in pursuit of Bose-Einstein condensation. Bose-Einstein condensation was reported in 1995, and this prize came along actually in 1997, which is about as quickly as they could. They gave it not for Bose-Einstein condensation, but for laser cooling, because they knew that was essential for Bose-Einstein condensation. Steve Chu had worked for Eugene Cummins, who was a student of Robbie. Claude Contanucci was a student of Alfred Casler, and Bill Phillips was a grandson of Norman Ramsey. So they all have firm, close connections to the Stern-Robbie tree. And then the discovery of Bose-Einstein condensation, the prize for that came in 2001. Eric Cornell had been a student of Dave Pritchard. Now, Dave Pritchard and I Dave Pritchard was my graduate student. The two of us became colleagues at MIT, and he taught Cornell. So there's a link. I mean, the spirit of Norman Ramsey was present everywhere then at MIT. It still is in a sense. Wolfgang Ketterle, who was a student of Robbie, a student of Pritchard rather, anyway, has that connection to Robbie. And Carl Wyman, who was a student of Ted Hench, who got the Nobel Prize, who had been a student of Arthur Shallow. So there's the connection, direct connection back to the roots. John Hall, there is no real direct connection there, but where he was working at NIST, he isn't an intermediate step on the family tree, but should be certainly acknowledged for his high precision measurements. And Ted Hench, who really invented laser spectroscopy and showed how to use it, got the Nobel Prize for the invention of the optical frequency cone, which allowed people to treat light like they treated microwaves in the past. And finally, there's Serge Haroche. Haroche was a student of Kohn Tanucci, who was a student of Casler. What Serge Haroche did was reverse what optical pumping had been designed to do, which was to show the effect of light on atoms. And he found out how to use atoms to affect the properties of light and do the most remarkable things. Dave Weinland was a student of Ramsey's, and he learned how to use ion traps to manipulate and hold ions. So I've also included Ray Weiss. Now, he is not an AMO physicist, but he was a student of Zacharias, who was maybe the first postdoc assistant that Robbie had. So there's very close connections to Robbie, to the style of doing things, for the attitudes and for the way the laboratory was run. So I think it's fair to say that that he's an honorary member of the AMO community. He is a distinguished member of the gravitational community, which was transformed by the discovery of gravitational waves with LIGO. So this is a wonderful example of how the knowledge in physics propagates and starts new things. So here is a diagram showing all of these things and all of these connections. Now, what one should take away from this is, first of all, it's good to be lucky. For most of these cases, the prizes could have gone elsewhere, or there were other people. Nonetheless, these lines of direct connection show how a subculture propagates and forms itself. Now, this subculture of AMO physics is now a very distinguished one. Anyone who makes a list of the few top areas in physics would include AMO physics these days. So it's an honor to be a member of that community. I'm very happy to be one. Not only because of the great work the community does, but the great people who do it. So I'm very grateful for that. And I think actually all scientists should be grateful to be in a society which supports them for doing what they want to do. And in all fairness, gets paid back many folds by the contributions to society, which pop out of research on totally irrelevant issues. One can't think of anything less important to the public welfare than gravitational waves. And yet, that has created a new field in physics, and new physicists are going to come out of that. Another example was the creation of atomic clocks, which gave rise to the global positioning system. The search wasn't to make a better navigational system. The search was to confirm a prediction by Einstein of general relativity. One can hardly think of a less useful thing to try to do, but it became useful in spite of itself. So this is sort of the end of the message that I wanted to deliver, that that we are members of a wonderful community, and we should all be appreciative of that. So, thank you. Oops.
Thank you very much, Dan, for the nice talk and give us this pathway from the very beginning to now. But that's not the end of the story, right? We still believe that with atomic physics and the quantum fluids and everything, we may reach even further in this chain that you present in your last slide, right?
Well, yeah. In fact, the meaning of AMO physics has really changed because it's become so broad that other fields have joined it. Condensed matter physicists now do their experiments and studies with ultra-cold atoms. It's been a real cultural upheaval which has come out of all of this research. And that's very exciting, and that's very hopeful. And it's a good time to be hopeful. So it's a good time to be a scientist.
Great. So we're going to open for questions. First of all, for the people that are here in the auditorium, is there any question you want to place for Dan Kleppner? Yeah, please. We're going to first make available for the people in the auditorium and then for the ones in the YouTube.
Hello, Kleppner. My name is Lukas Gustavo. And I would like to ask about, you painted a pantheon of ideas and people that shaped the current understanding of physics. So translating that to now, what are the next great ideas that are fermenting now or have recently fermented that you think that will change physics as a whole?
Well, I used to say that if I knew what that was, I'd be rushing out to do it. But I'm not rushing out to do things these days because I've gotten kind of old. You can't predict it. When Bose-Einstein condensation was discovered, I don't think anyone had any idea of the flowering of physics which had come out of that discovery. That's one of the excitements of physics. You start studying one thing, you learn new things, and new areas grow up. I mean, who could believe that you could hold atoms in space in optical lattices and play games with them and observe all sorts of phenomena predicted by the condensed matter theorists? It's simply incredible. And simply incredible things will be happening in the future. The best thing is to look at a problem which you think is a worthy problem in itself and pursue it. And you're likely to have a happy surprise.
Thank you. Hello, Daniel. I'm Dalila. I would like to ask, since you you were close to all these people, to at least some of them that you were talk about. Is there any characteristic or think about their personality, way of thinking, among all these people that you recommend for us to pursue to become better scientists? Thank you.
You got the
Well,
question then?
I gather what you're asking is what are the qualities that you look for in trying to find promising science?
That's right, to become a good scientist.
Yeah. Well, as a role model for that, you've seen one today in Bill Phillips. As a graduate student, he was just terrific. He was very bright, very energetic, and rather smart. When he graduated, I encouraged him to take a university position because, as you can see, he would be a great professor. He ignored me. He went to NIST, the Bureau of Standards at the time, and he had his own vision of what to do. Actually, he told me that the vision was because of what Dave Weinland had done at NIST in building his own research group. So Bill did that. He worked on the things that interested NIST first. There was a very good director, and when he asked to move in a new direction, that was supported. So that's a wonderful success story. And so part of being successful is knowing when to ignore the advice of your advisor. Yeah.
So you see, you cannot listen all the words of your advice, but listen the majority of them. Okay, any further question from the auditorium? Oh, I have here one question that came in the YouTube. And Steiner and Gerlach experiment is an example that we cannot only find what we expected. So what is your advice for when we're doing experiment? We should look much behind what we expected?
Yeah. Well, first of all, one wants to work on problems which you think are really interesting. All these problems that Stern pursued were really interesting. You never know what you're going to find. He had the good fortune to find a series of very important things. But you have to, well, Robbie was famous at Columbia for stopping students going down the hall, graduate students, and asking them what they were doing. And he would generally say, "Why are you doing that?" It's a rather hostile answer. But the student should be able to give an answer on that. So whatever you're doing, you want to know why you're doing it. So that's one piece of advice. I can't say I've always followed it myself. Sometimes I've done things just because they look like fun. But in searching for Bose-Einstein condensation, which I was involved in its early days, it was very clear this was a fascinating phenomenon which had never been observed. So that should take care of itself. On cavity QED, which grew out of work, I helped start that in working on trying to suppress spontaneous emission, which seemed to me like a very novel thing, and just following the principles really laid out by Einstein. One should be able to do that. And we did demonstrate it. Randy Hewlett showed it in our laboratory. But having demonstrated suppressing spontaneous emission, the interest turned over to the other extreme of enhancing spontaneous emission, which Serge Haroche has done very well by putting atoms in cavities. So I got interested in that just because it kind of looked like fun to play around with at first. I had no idea what was going to come out of it. I mean, Serge's experiments are unbelievable. They are going to have practical use sometime. I'm not sure how. In any case, a series of really excellent physicists have come out of his laboratory. So just the teaching function of research is a valuable function that should be appreciated. So.
Okay, Dan, thank you. Now, I have my own question here. We know that the development of techniques with the molecular beams really was a revolution for understanding atomic physics and basically took us from understanding the atom to put them in traps and everything. And now, just to make a parallel, the Bose-Einstein condensation is another technique that is going much beyond what we thought in the very beginning as an example of phase transition. So Bose-Einstein condensation is reaching almost all the fields of physics and chemistry, even though we are not deep in chemistry yet, but I believe we're going to be. Can you comment on this? Do you believe that producing quantum fluids the way we are now can really be a pathway to much more discoveries on the future?
Exactly. I can't imagine it not having huge consequences. In discovering Bose-Einstein condensation, we were really just looking for that, to see that effect. But the reason that behind it interest was that you knew that something new and important would come out of this. And we still can't judge the extent of this. The field has simply changed physics. I realized that when our department decided it needed a new condensed matter physicist, so the condensed matter division ran a search for condensed matter physicists. The three first top people on their list all wanted to do condensed matter physics with ultra-cold atoms, and we appointed one of them. To me, that just showed how much the fields have been changed in a very short time because of this discovery. Now, such discoveries don't come along too often, but they do come along. And the knowledge that you may be able to do this is certainly stimulating. Of course, along with that stimulation, you have to be pretty good about failures. Lots of work fails, but then you just try again. So you need tenacity to really achieve something. So tenacity, vigor, and intelligence are all qualities that are to be esteemed. And to me, it's interesting that this huge explosion right now was triggered by Bose-Einstein condensation. There again, we have Einstein as the great-grandfather of us all, particularly of our field. He is one of the grandfathers. It's worth reading his papers. I mean, some are very difficult to deal with, but many of them are amazingly simple and straightforward. All of them have been translated. His paper on the spontaneous and stimulated emission is a pleasure to read. It's so exciting to see his mind at work. So you want to become scientifically literate, which means reading more than the latest PhysRev letter or archive entry.
Okay, well, thank you. That's a great motivation for the field. And any further questions? one more here, so.
Hello, Daniel. I'm Pedro, and I wanted to ask you if you have any advice for us that want to become good mentors, such as yourself.
I'm sorry, I didn't understand the question.
Good advice to become a good mentor,
To become a,
like you.
oh, well, a good mentor is someone who really wants to help the student. You help the student by trying to give good advice if he asks for advice, about people and subjects to work on. And he should promote your entry into the field. Going to conferences is one very powerful way to become at home in a field and become known. Otto Stern never put his name first on the papers. In fact, one of the last things they did, the measurement of the reflection of the light, the paper was by Frisch. Stern's name isn't on the paper at all. The reason for that was that everyone was fleeing to the United States at that time. Frisch needed to get a position, and positions were difficult to obtain. Stern felt that if his name was on the paper, it would decrease the visibility of Frisch. So he just didn't put his name on the paper. Frisch did get a good job, but that's being a really good mentor. So if you really want to be a great mentor, do something great and just let the graduate student publish it on his own.
Okay, very nice. Then we want to thank you again for giving your time and giving the talk to us. It was a wonderful talk. And I will send you later the link so you can send it to others. Bill Phillips already asked me to send the link. He wants to see your talk later today. So we're going to do that. So thank you very much, and I hope to see you here in São Carlos in the coming future.
Hope so. Thanks for inviting me.
All right. Thank you very much. Let's give a thank you to them. Okay, so now we have a break for the coffee, and then we return for Thomas Kazenzer talk, and then David Preacher. Thank you very much. Have a good day, Dan. Thank you very much.
Thank you.